All right, Module 26 is exciting because we're introducing a brand new kind of reagent um, that is really powerful and really widespread. Um, and that is, uh, they're going to be called organometallic reagents. They involve carbon bonding to a metal, which is not something that you're used to seeing. Um, so I'm going to open by introducing what we call a carbanion. Um, that would be a carbon with a negative charge. So if I start with an alkane and I were to try to remove a proton using a base, um, I could create this carbon with a negative charge. Now that's really hard to do. It's really hard to do because carbon's not very electronegative. And if you remember from your pKa list, the pKa for an alkane is close to 50. Um, that's super high, meaning we don't actually have a base strong enough to do this. Okay. So this base in quotes, in fact, there is no base that can actually do this to make this carbanion. Um, but we might want to create a carbanion so that we could use it as a nucleophile, um, so that one carbon could attack another carbon to make carbon-carbon bonds. Or we might want to create a really strong base that behaves like a carbanion. So what we're going to do to get there is we're going to use some magic. And when I say magic, I'm not referring to real magic, but the idea is if we can get carbon to bond to a metal, remember metals have really low electronegativity. So a bond between carbon and a metal is going to be very polarized toward the carbon, meaning that carbon will have lots of partial negative charge. Um, and, in this intro level of organic chemistry, you usually don't go into great detail about how these things work. And that's why I'm calling them magic. Um, but there are entire courses devoted to organometallic chemistry. So you can definitely learn this at a deeper level at some point. Um, but the idea is we're going to use metals and try and get them to bond to carbon. And one of the ways we found to do that is to start with this functional group over here, which you remember is an alkyl halide. Um, and remember, an alkyl halide, if we're considering the oxidation level of this carbon here, the oxidation level is 1. Uh, but what we'd like to do is reduce that. And if you consider a carbanion, the oxidation level of a carbanion, since we've put a negative charge on it, it's even one level lower than an alkane. So this would be like -1. Um, so we want to essentially add 2 electrons to our carbon. Um, and the way we're going to do that um, is we're going to use something that has electrons to give away. So magnesium metal, magnesium is in the second column of the periodic table, which means usually when it forms bonds, it loses 2 electrons. And so it's going to carry out that transition where it takes the carbon down from level 1 to level -1, essentially. Um, we can do the same thing with lithium. Lithium's in the first column, so we need 2 equivalents of lithium to make this happen. Um, but what happens is the metal sort of inserts itself between the carbon and the halide. And by inserting itself between the carbon and the halide, um, it is creating a metal to carbon bond. And that metal to carbon bond is going to behave um, as if it's polarized toward the carbon. So this will behave as if we have my carbon here with a negative charge and my magnesium bromide with a positive charge. So it behaves sort of like a carbanion. In reality, these things are bound up together. Usually, multiple of these molecules are kind of in a complex. Um, but at a simple level, we can treat it as if it's going to be a carbanion. This one here, the magnesium bromide, this one gets a special name. This one's named after a French chemist, Grignard. So this is called a Grignard reagent, or a magnesium bromide reagent. If we use lithium instead, we can make what we call an alkyl lithium reagent. And again, that's going to behave as if it's got a polarized bond. So it's almost like an ionic bond where you have a carbanion and then you have a lithium plus ion. In your first year, you'll probably encounter both Grignard reagents and alkyl lithium reagents. There are others that you may come across. This is not an exhaustive list, but just giving you some idea. Now, why do we need more than one type of these? Well, if you think about this in terms of how reactive they're going to be, that's going to depend on how electronegative this metal is that your carbon is bonded to. If you think about this list I'm showing you, it's really a list in increasing order of electronegativity. Of the metal. So over here on the left with alkyl lithium, lithium has a very, very low electronegativity. So this is going to be the most reactive. Because it's really the most polarized carbon metal bond. So it's the most ionic carbon metal bond. And then at this end, we'll have less reactive ones. And that just has to do with the fact that the more carbanion character you have, the more reactive that reagent's going to be. So you will see various organometallic reagents in your chemistry career. Electronegativity plays a role, just like we've seen in various circumstances. So that's a little bit about what organometallic compounds are. Let's talk about some of the ways we might use them. The first way is as very strong bases. One commonly used very strong base is called N-butyl lithium. Often abbreviated as N-buty. This is a very strong base, and sometimes we might use that to deprotonate something that has a very high pKa. So one example would be this compound here. If I have an amine, that has a pKa of about 35, right? That is very hard to deprotonate, but if I use a carbanion, which has an even higher pKa, I can use that to deprotonate. Now, when we use these bases, or when we use these reagents in general, there's two ways people tend to draw them. Sometimes you can treat it as if this sigma bond is my donor. So I could have the sigma bond between carbon and lithium go and grab the proton. Sometimes in mechanisms, we might also just draw it like this as an abbreviation and have that arrow originate at the lone pair on carbon. In my view, both of those are acceptable. Some instructors might have different views. But we can use N-butyl lithium as a very strong base That, of course, just creates butane as a side product. Um, and more importantly, it deprotonates my amine. Um, and creates this strong amine base. This is one that we have a specific use for that you might learn in a second semester organic chemistry class. This is known as lithium diisobutyl amide, LDA for abbreviation, and we make that using butyl lithium usually. Um, Another way that we might use these is if we want to mark a carbon by adding a hydrogen, a heavy hydrogen. I'm a fan of this word, deuteration. Um, Remember, deuteration, this means adding deuterium. I think you've encountered deuterium at some point. Deuterium, which we abbreviate with D often, is just hydrogen with a neutron in it. So it's heavy hydrogen. But if I have a compound, and let's say I want to put a deuterium in a specific spot, this can often be useful so that you can track how where hydrogens get moved during reactions. Um, it can be used for kinetic studies to test reaction rates. How does replacing a hydrogen with deuterium affect the reaction rate? And that can give you insight into mechanisms. But if you want to add a deuterium to a compound, you can say add magnesium to an alkyl halide, make your Grignard reagent, and then react that with D2O, so what we call heavy water, and you can replace that alkyl halide with a deuterium on that carbon. Um, so that is also a use. Sorry, one thing I glossed over a little earlier. I'm listing this ether solvent here, and I forgot to talk about why we use an ether solvent. Um, so the purpose of using the ether solvent is that this is at least somewhat polar, um, which supports that formation of the polar bond between the metal and carbon, but it doesn't have any acidic protons. So it's kind of important that we use a solvent here that doesn't have any acidic protons. If you were to try and um, make a Grignard reagent in water, immediately, since a Grignard reagent is a very strong base, it would just grab a proton from that water. And in fact, if you try to make a Grignard reagent on a humid day, a lot of times your reaction fails because that Grignard reagent is such a strong base. It just grabs whatever acidic proton is around. So this ether solvent is listed here just to indicate, okay, we need a, a solvent that doesn't have any acidic protons. Um, because as soon as a Grignard reagent meets an acidic proton, it's going to grab it. So you can use this to mark a reaction, a particular substrate with deuterium in place of a hydrogen. Um, that's something that it could be used for. Uh, the biggest use, what we really want these for, is as nucleophiles, because as a nucleophile, since the negative charge is on carbon, it can now form carbon-carbon bonds. And organic chemists are in the business of building up bigger molecules from smaller ones. If you want to build bigger molecules, you want to extend your backbone, you need to form new carbon-carbon bonds. So some examples of this would be I can react a Grignard reagent with, let's say, a ketone to form a new carbon-carbon bond. This is my new carbon-carbon bond. I can react a Grignard reagent with an epoxide. And form a new carbon-carbon bond. And so this is the real power of these particular organometallic compounds. And so what they react with specifically takes a while to explain, because they react with certain functional groups and not with others. And so I'm just giving a couple of examples here. I'm going to go on to elaborate on this reaction between a Grignard reagent and an epoxide right now. In future units, you would learn about reactions between Grignard reagents and carbonyl compounds like this one. But I'm just introducing these as a couple of examples of how these reagents can be used to make new carbon-carbon bonds. So this is just a couple examples. And there's more to come. So don't think you need to remember these two examples that I just showed. I'm gonna elaborate on the use of Grignard reagents with epoxides next. All right, so let's look specifically at how we can open epoxides with a Grignard reagent. So let's say I started with an alkene and I wanted to extend my carbon chain by one. So counting carbons is hugely important as you go forward, particularly when you're thinking about synthesis problems. So I'm starting here with a carbon chain that has 5 carbons. And I'm ending with a carbon chain that has a 6th carbon added. Okay. So my 6th carbon is coming from this Grignard reagent here. I'm not going to show the mechanism for the MCPBA step. You've already done that. But let's talk about what's going on in this second step. Notice I have 2 arrows here. I have my Grignard reagent over 1 arrow, and then I have what's called an H plus workup. Remember that the Grignard reagent cannot be around any acidic protons, because if it is, it's just going to grab that proton, and now my Grignard reagent is what we call quenched. It just turns into an alkane. So I want to avoid that. So generally, this reaction is done under conditions where you have no water around, no alcohols around, nothing around that could be a source of protons. Again, I have my Grignard reagent that has this carbon magnesium bond. And like I said, for me, if you were to draw this mechanism using that as your donor to attack, that's one way to show it. But if you also were to show it with a carbanion as your nucleophile, I would find that acceptable. Now, my epoxide here is not symmetrical. There are 2 spots where I could attack my epoxide. What we saw earlier is when, in Module 25, when we attack epoxides, we have different results if we do it in acidic or basic conditions. Remember that the Grignard is very basic, so this step here happens under basic conditions, very basic conditions. When we said under basic conditions, it's really the nucleophile who's in charge. The epoxide is an okay electrophile, but the nucleophile is the one that's really in charge, and it's going to attack whatever the most accessible sigma star is. So here we're going to attack the more accessible or the less substituted carbon of the epoxide. So I attack that less substituted carbon. And when I do that, I'm going to break this sigma CO bond. And that's going to make a new carbon-carbon bond. So now I have 6, 1, 2, 3, 4, 5. I've made my new carbon-carbon bond here. And I'm left with a negative oxygen on carbon 2 because I didn't break the bond between carbon 2 and oxygen. I often draw this with the magnesium bromide next to it because it's not really a free O minus. It's not like a free alk oxide here. It's going to be bound up with that magnesium, and it's going to stay in that state until I let my reaction finish. And that's when I'm going to do a second step where I add enough acid to neutralize my solution. All right. Whenever you see H plus workup as a second step, that workup just means, okay, add enough acid to neutralize the solution. You're not making the solution acidic. You're not adding a whole bunch of excess acid, but enough to neutralize the solution. What that does is, first of all, when you start adding acid, any excess Grignard reagent you have immediately is going to react with that acid. So it gets rid of your excess Grignard first, and then it will reprotonate this alkoxide. So my second step is to reprotonate that alkoxide and form an alcohol. So notice the overall sequence here is that we took an epoxide. We did step 1, Grignard reagent. Step 2, acid workup. And we made an alcohol. So if you're still making a chart of your reactions, then your starting material here would be epoxide. Your reagents, this would be 2 separate steps, Grignard reagent followed by an acid workup. And your product is an alcohol, and your alcohol has a new carbon-carbon bond next door. When I say next door, here's my new carbon-carbon bond. Here's my OH group. They're on neighboring carbons. So from a synthetic standpoint, that's the way you want to think about this reaction sequence. All right, so take a moment, try and predict the product of this step that I've shown you. So pause the video, try and draw the mechanism here for this step, try and predict what the product looks like, think about stereochemistry, and then come back in a moment. All right, one of the first things I did was I numbered my carbons. It doesn't necessarily matter how you number them. I thought a little bit ahead in my numbering scheme, but I don't always, and you don't have to. As long as you're consistent when you draw the product, think about where each numbered carbon goes. Um, so I thought about this and I said, well, this epoxide is not symmetrical. The carbon 5, the way I've designated it, is going to be the more accessible side. So when my Grignard reagent attacks, it's going to attack that more accessible side. So when I do that, now I'm going to have carbon 5, 6. Nothing happens at carbon 6. So the stereochemistry at carbon 6 is going to stay the same. But I'm breaking the bond between 5 and oxygen. I still have a bond between 6 and oxygen. So I have 7, 6, 5. And now I have a new carbon-carbon bond between 5 and 4. And then 4 is still bonded to 3, still bonded to 2, still bonded to 1. So when I say I thought ahead a little bit in my numbering, I ended up with a chain that is continuously numbered. And carbon 2 still has those 2 methyl groups on it. All right, so stereochemistry at 6 stayed the same, and I made my new carbon-carbon bond between 4 and 5. And then when I do the acid workup step, that is when I'm going to get to this final product, which is my alcohol. One, two, three, 4, 5, 6, 7. So there is my product. So hopefully you were able to draw something like that. But let me know if you have questions about that outcome. I'm going to wrap up the first part of Module 26 there. And the next part is how do we apply this in synthesis? So that's where it gets fun.